Hello, everyone. So thanks again, the organizers, for this great workshop. So for me, it's actually my first real-life conference, so I'm super excited to present my work. So my work is about exploration beyond bandits. So as we all know, we all have to explore all the time in our everyday lives. So from where to go to dinner to which workshop to attend at a conference, we often have to decide between the current best option and other less well-known possibilities. Oops. No, okay. And this has often been studied in multi-armed bandits, and research mostly focused on simple uncertainty-guided strategies that could be directed or random. However, we think that humans in their real lives also use more sophisticated strategies than that. And this becomes obvious when looking at some of the activities that we do in our everyday life. So these are some of the activities that I personally enjoy doing. And we can see that in all of them, we display some exploration behavior that cannot easily be described with simple uncertainty-guided strategies. So as I already said, we think humans also use more sophisticated strategies. And some strategies that we think humans use for exploration are fun, empowerment, and goal condition strategies. So fun intuitively influences how we behave, as we often decide what to do based on if we think it would be fun to do. So just think about your last days at this conference. I bet you made several decisions based on what you thought would be a fun thing to do. And we now believe that we can describe fun as learning progress. So how much people improve their model of the environment, which is very much related to what we already heard in the panel discussion before lunch. And another important concept that we think humans use for their exploration behavior is empowerment. So empowerment for us is the idea that we explore to explore even more in the future. So we ideally explore options that can generate even more options in the future. And this, for example, is done in science when people are researching methods to produce vaccines, for example, even faster and even more different ones in the future. And they're already researching the methods for that right now. And now, these strategies cannot easily be studied with simple multi-armed bandits. So this opens up a vision where we extend current paradigms by using games to test how people explore and learn in these more complex paradigms. So that's basically what we want to do in our work. So now let's come to the first project about fun. So according to Jürgen Schmidhuber, fun is the intrinsic reward of making progress and learning the model of the world. So as we already heard in the panel discussion before lunch, so the idea of this learning progress hypothesis is the more your model improves, the more fun you have. So it's by definition a linear relationship. And then we assume that with medium difficulty, we also make the most model improvement. So this was, for example, shown in the 85% learning group paper by Wilson, but we also could see that in our own simulations. And now we want to test that with medium difficulty, we also have the most fun when we act in an environment. So we see this inverse U-shaped pattern. Now the question is, what is difficulty here? So we think it's a mismatch between what's in your mind and what's in the environment. So this could, for example, be a skill that you have versus a skill that's required, or your prior of learning and the environment. And we now want to formalize this theory further and also test it in some online game data sets, but also in our own small experiments. So 3 games that we want to have a look at are these ones here. So the first one is called Super Mario Maker. So the idea is that people can create Super Mario levels and other people can play and rate them. Then the second game is called Robosso. Here players have to navigate a spaceship through a maze by writing small recursive programs. And then the third one is called Trackmania, and here people can create racetracks and other people can play and rate them. And the advantages of using this online game data sets is that people play these games voluntarily. So we don't have to pay them any performance-dependent bonus. more people play it, they play it more often, and they also play it longer. So we have more data than by just using in-lab experiments. There are some disadvantages. So we don't have all the data we would like to have in these cases. So we don't have the individual play histories of all the players, which would have been nice. And also we don't have consistent fun and difficulty measures throughout the different games. So we have to approximate that for each game individually. So now you can see that we have a lot of different levels per game and also a lot of different high number of ratings. And now, as I said, we had to somehow approximate a fun measure. So for the first two games, we used the average like rate. So basically how probable people were to give a certain level a like. And for the third game, we used the absolute number of awards, which is basically also a like. And for the difficulty measure, we used the solve rate for the first two, so how probable people were to finish a level once they started it. And for the third game, we just had 4 difficulty categories given. And now when we plot the difficulty on the x-axis and our fun measure on the y-axis, we can see an inverse U-shaped pattern in each of these games as we would expect. Now, ideally, we would like to go a bit more into detail with that, but as I said, we don't have all the data that we will need. So instead, we decided to program our own small experiment to research all of this in a more controlled environment. And for that, we use the guessing game. So the idea here is that you are stranded on an alien planet and you have to wait until your spaceship is fully refueled. So you find yourself you find that you need to pass some time, and you do that on an alien playground, which has a lot of machines looking like this on it. And each machine produces numbers from a Gaussian distribution with a certain fixed mean and variance. And now you can guess with each machine as long as you want to. And if you don't want to continue, you can just go on to the next machine. The only requirement is that you make at least 3 guesses per machine. And the experiment ends after 10 minutes, no matter how many guesses you make per machine or with how many machines you played. And our fun measure here is how much people engage with each machine. So yeah, how many guesses they make per each one. And what's really important here is that we don't give players an exact goal. So we don't tell them to be as close as possible. We don't pay them any performance-dependent bonus. We just tell them, if you want to continue guessing with this machine, do so. If you don't want to, you can just go on to the next one. And as I already said, these machines are producing numbers from a Gaussian distribution. So we sampled the mean of this distribution randomly between 20 and 80. And the variance of these distributions have one of these 5 values. So if people act with a machine in a variance 0.1 condition, it will be super simple for them because the machine will just generate the same number almost every time over and over again. So it should be very easy for them to guess the right number every time. Then if they're on the contrary in the variance 1000 condition, it would be very hard for them to guess the right number as the machine would generate every number almost with equal probability. So if people now care only about being right, they should spend most time in variance 0.1 condition. But if they act according to our fun measure, they should spend most of their time in some intermediate variant machine. And now we want to simulate that. So for that, we use a computational model based on this theory of learning progress. And the idea is that a rational agent guesses until their learning progress, so their update of the mean, lies below a certain threshold. So their update of the mean has converged. And for the simulation, we use a Kalman filter where we have a prior of the mean and prior of the variance. And with each sample, the Kalman filter updates this mean and the variance. And if the mean lies below this predefined threshold, the simulation stops. And we plotted this for each prior variance ranging from 0.1 to 1000, as you can see here in the 5 panels. And we plotted the true variance on the x-axis and the number of guesses on the y-axis. And the prior variance is indicated by the gray line in each panel. And as you can see, we always have this inverted U shape just with a shifted mean. And we can also see that the best variance, so the one which makes significant updates for the most time steps, is most often the one which is a bit higher than the prior. And now we wanted to see how humans behave in this game. So we ran an experiment on mTurk with 99 participants. And again, here we plot the true variance on the x-axis and the average number of guesses on the y-axis. And we can see an inverse U-shape as we would expect. And the peak lies at the variance of 1. So apparently they like to interact with the variance 1 machine the most. So it might have been the case that their prior of the participants was a bit smaller than 1. Now on the right, you can see we use for our regression analysis a mixed effects model where we use the log of the engagement and the variance scale discretely from 0 to 4. And we have a significant negative effect of the variance squared, which accounts for this inverse U-shape. So that was the fun project. And now we want to continue this work, for example, by manipulating the priors of the participants to see if that really influences their fun preferences in the different environments. So these would be the next steps. Now, I would like to come to our second project in this area, which is about empowerment. So as I already said, empowerment for us is the idea that you explore even more in the future, or you explore the options that can generate even more options in the future. And to do this, we use the game Little Alchemy. Perhaps some of you know it. It's a smartphone game and it's quite popular. So it has over 10 million downloads on Google Play. And the idea is that you have a set of elements. So in the beginning, it's only air, earth, fire, and water. And you can combine always 2 elements, and sometimes that creates a new one. So over time, your inventory grows and you get a world filled with different elements ranging from dinosaurs to Ninja Turtles. And the whole game consists of 720 elements, around which around 3,500 combinations are successful. And this is one example how this can go. So you can combine fire and earth, which creates lava. Lava with sea together gives you primordial soup. And with some steps in between, you can create life, and life and clay together gives you, of course, human. So we have a data set of over 29,000 players, and they tried around 6 million combinations. So we could see that people really liked the game. So they played on average 160 trials and found on average 50 elements, but some players really put thousands of trials into the game and managed to find all 720 elements. And we wanted to see how do humans play this game, and we think that empowerment could be a strategy that they use to decide on which elements to combine. And empowerment in this game is that how many more elements a certain element can produce by combination with other elements. So in this example here, human is way more empowering than alien, as it can lead to 83 more elements in the future, while alien can lead only to 1. And now we wanted to see if in the human player behavior, we already see some signatures for this empowerment value. And so we looked at the data and we saw that the probability of immediately using an element once it was created is higher the empowerment value of this element is. So that's the blue line here. And this becomes even more evident when comparing that to a random model, which just picks 2 elements at random. Here we don't see such a dependency. And we created 4 different models to compare. So the first one is just the baseline, a random model, which picks 2 elements at random. Then we have our oracle model, which is the upper limit, which just picks the next successful combination according to the true game tree. Then we have an uncertainty model, which picks the next combinations with elements that have rarely been used in the past for combinations. And then we have our empowerment model, which picks the next combination based on how empowering the resulting elements will be. And we let them all run for 200 time steps and simulated each one 1,000 times. And we can see that the uncertainty model performs only slightly better than our baseline model, while the oracle and the empowerment model outperform human behavior here. But that is not a surprise at all, because both of them use the true game tree to generate their predictions. So of course, if we want to really model human behavior, we can't do that in this way. So we think instead humans have some kind of intuitions about which elements are combinable and which elements are empowering. So they use these intuitions to somehow guide their decisions. And so we wanted to model these intuitions so that we can use them for our empowerment model. And so we use 2 neural networks for that. Okay, cool. So we use vector representations incorporating the semantic knowledge of the elements as inputs. And then the first neural net is our link prediction model, which just predicts how likely the current combination is resulting in an element. And the second neural net is then assigning a probability to each possible element, how likely it is to be the resulting element of this combination. And we train these neural nets on the true game tree with cross-validation by leaving out some combinations for the test set. And we only use the predictions of this test set to then recreate our game tree according to the predictions of the neural net. And we also validated that in a small experiment on mTurk, and we saw that human intuitions do correlate with the predictions of this network. And now we wanted to see how humans play the game. So we performed a bottom-up regression analysis with a mixed effects model, and we let it run on all of the trials that we had of participants and controlled for the trial number. And we could see that the best model is a combination of the empowerment and the uncertainty model. So it really seems to be the case that humans use more elaborated strategies than just uncertainty to guide their decisions in this game. Now, one question that remained for us was, could we have seen this behavior already in simpler paradigms? So do we really need this complex game to find empowerment behavior in humans? And to do that, we created two simpler experiments. So Tiny Alchemy is basically the same thing as Little Alchemy, just as a version for mTurk. And then we created Tiny Pixels, which is the same game, but has no semantic information, neither in the pictures nor in the words. And we could see that people obviously liked the Tiny Alchemy version more, so they played around 460 trials on average versus 160 in the other game. And they found on average 90 elements versus only 30 elements in the Tiny Pixels case. And now we did the same analysis as we did before in the real game, and we could see that in Tiny Alchemy, again, empowerment played a big role in their decisions, while in Tiny Pixels, it did not. So indeed, we need this more elaborated paradigms that include, for example, the semantic structure to see this more complex behavior in humans. And now I'm at the end of my talk. So we studied, as a conclusion, we studied two intrinsic motivations. One is fun is learning progress, and the other one is empowerment, which we see as exploration to explore more. And as methods, we use online game data sets as well as gamified mTurk studies. And our goal is to enrich paradigms and models of human exploration by using games. And yeah, we hope that this work got us somewhat closer to understanding a little bit better how humans explore in their everyday lives. And I quickly want to thank my collaborators on this project, especially Eric Schulz, as well as the Max Planck Society, the Volkswagen Foundation, and the Jacobs Foundation for funding this work. And yeah, thank you all for listening.